Okay, so we're going to talk today about the graphs of the other trigonometric functions, and we're going to start with tangent. Now, before I show you the graph of the tangent function, I want to remind you that the tangent function is defined to be sine over cosine. So this has got some implications for the domain. What this means is that it has some implications for the domain of tangent. So tangent is undefined wherever the cosine function equals 0, because we cannot divide by 0. It's undefined. And so you'll remember from previous coursework that this means that we should see a vertical asymptote at those points. And you'll remember from our previous conversation, the cosine equals 0 at multiples of pi over 2. Well, at odd multiples of pi over 2, right? So we're going to have vertical asymptotes wherever x equals k pi over 2, where k equals positive and negative 1, 3, 5, and so on. And so based just on the way that tangent is defined, we should also expect to see the tangent of x is going to equal 0 where the sine function equals 0, because of the way the tangent is defined. And you'll remember that sine goes through 0, so we expect to find x-intercepts where x equals k pi, where k is 0, 1, 2, in other words, any positive or negative integer. Okay, so let's take a look at the graph of tangent. And then we'll talk about some more things about this curve. And I'm going to make my x-axis show me pi over 2's. Okay. And sure enough, we see what we expected to see, yeah? We see that at pi over 2 and negative pi over 2 and negative 3 pi over 2 and positive 3 pi over 2, in other words, all the odd multiples of pi over 2, we have vertical asymptotes. Tangent actually shoots off into infinity. And we see that we have x-intercepts at our integer multiples of pi. Now, some other things to notice. The tangent function goes through this point right here. And this point is pi over 4, 1. Because the tangent of pi over 4 is 1. And we can also see that we've got negative pi over 4, negative 1, and 3 pi over 4, negative 1, and 5 pi over 4, 1. And if we keep going, this is 9 pi over 4, 1. What you're seeing is that tangent repeats itself every pi units. So the tangent function, I'm going to give you, has got a period of pi, as opposed to 2 pi for sine and cosine. So this is a little different, a little unique, and we need to remember this. We can't really talk about the amplitude of the tangent function because there's really no amplitude to be seen, right? We can talk about a vertical stretch and a horizontal stretch, and I'll explain that to you in a minute. The domain of the tangent function is x, it's all x's except for pi over 2 plus k pi. Now this is just another way of saying what I said a minute ago. This just gets you the odd multiples of pi over 2. But it allows k to be any integer. Now the range of tangent is all real numbers. Okay. So let's take a look at some of the transformations of tangent. And the internal, so most of them function the way you would expect. In other words, you can have f of x equals a times the tangent of bx plus c. We don't think of a as amplitude, we think of a as giving us a vertical shift. Well, not a vertical shift. It gives us a vertical stretch or compression is what it does. It stretches our function vertically. And I'm going to show you this in action here in a second. Now, B is related to the observed period. So my period is going to be not 2 pi, but pi over B. And the reason for that is because the natural period of tangent is pi. So our period is related to that natural period, that pi. Okay. And it'll have a midline at the line y equals c. So let's modify my Desmos curve a little bit. Whoops. Okay. So I'm going to stay centered at the midline, at the origin, at the x-axis here for a minute. And so how do you know where your midline is? Well, you can kind of see the curvature change. So if we look right here, the function curves down. If we look right here, the function curves up. And that's kind of what you're looking for, is kind of the center point of this elongated S curve. Now, this can be kind of hard to see. So one way you can think about this is to look for your function, your angle that would be equivalent to your pi over 4 and your 1 and your negative 1. Now, that's not exact either. Sometimes with tangent, we just have to do some trial and error. And I'm going to walk you through some examples in the next video here. But I want to put a point on here, and I'm going to do this before. Okay, that's good. Okay, I'm going to put on the point. Let's do this. Let's do pi over 4. Make this a function. And we're going to label this guy. Okay. And I'm doing this because I want you to watch what happens here. So I'm going to also put a non-moving one on. Okay. So the red point is going to be, and in fact, I'm going to do this. Okay, so what I've done is I've just put a dotted reference unadulterated tangent curve on so that we can see what happens. So I'm going to make my vertical stretch, my external multiplier be 2. And notice what happens. My curve gets steeper, right? It's stretched vertically. The point that was at 1 is moved up a unit. And if I make it be 3, the same thing happens. Now what happens if I make this be 1/2? Well, then my curve gets shorter and fatter, just like we remember from Math 111. Because really what we're talking about are transformations. Okay, so let's put this guy back to 1. Now, and what happens if I make it be negative? Well, if I make it be negative, it turns the curve upside down. So let me go with -1. And notice what it does. It turns it upside down, reflects it across the x-axis. Okay. We're going to do some work with B. We're going to limit ourselves to this, and I'm going to actually do this because I want to make a point here. Okay. So if my internal multiplier, no, that's not what I want to do, sorry. There, that'll work. Okay. So if my internal multiplier is 1, then I've got my standard sorry, let me silence this. I've got my standard tangent curve. If my internal multiplier is 2, what's that going to do? Well, let's see. So it's harder to see here. Let's go find that point. Where's my black point? My pi over 4. Go away. Well, it's the same place, right? No, it's not. Where is it? It's going to be at pi over 2, right? It should be. So what I want you to notice is this. So the period on this function with an internal multiplier is not pi, but pi over 2, because the observed period is the natural period divided by the internal multiplier. What happens if I make this be smaller? Well, you can see what happens. We spread out our solid curves. So the period becomes, in this case, it would be, it repeats itself every 2 pi units. Okay, so let's work a couple of examples in the next video.